About CSS4 color. I guess you all know about CSS and you all know about CSS3 color. You all know all that stuff, you know, hashes and RGB parens and all that stuff. And I'm one of the editors of CSS4 color. And the problem that I find is not that people don't understand the syntax, but they say to me, yeah, Chris, this is great, but what does it all mean? Why would I want to use this? What can I do? So most of this talk is going to be about what is color. What can you do with color? And right at the end, don't worry, right at the end, we'll get back to CSS. Okay, so a quick bit about me. That's me, in case you were wondering. Not wearing a suit in this photo. I'm a technical director at the World Wide Web Consortium, W3C. I work for Tim Berners-Lee, who invented the web. And I started SVG, by which I mean I got the people together to actually make SVG, wrote the requirements document, and made sure that people actually kept going until it was finished. I also chaired the working group that produced it. I was one of the co-authors of the PNG format. I've worked in web fonts for a while. The group that did @FontFace, I chaired that. I've worked on WAF1 and WAF2, more recently chromatic fonts, multicolored fonts. But more relevantly for this talk, I was the first chair of the CSS working group. I'm currently the staff contact. I was one of the editors of CSS2, and in particular relevant, CSS4 color co-editor with Tab Atkins. So let's see, what are we going to talk about today? Well, first of all, we're going to cover some basics so we're all on the same page. Then we're going to talk about how do you measure color. Then I'm going to talk about something called CIE-LAB. Does anyone here know what that is already, by the way? Feel free to leave if so. No. Okay, good. Then I'm going to talk about measuring color displays and what you can do with color displays. Then, in case any of you use CSS for print, I'm going to talk about CMYK. And lastly, the actual relevant bit, I guess you could say, what does CSS4 color bring to this that you'll now know how to use? So, basics. What is that on screen? What is it? A prism. What does a prism do? It splits light. What happens when the light splits? It goes into different colors. That's right. How do you know it goes into different colors? Because you can see them. Right, now we have all the parts that we need. There's light, and it splits into colors, and we know that it does that because we can see it. What about bumblebees? You can see bumblebees. Thanks there for that, Bruce. Apart from being able to see bumblebees, can bumblebees see colors? Yes, they can. Do they see the same ones as us? No. What about snakes? They can see infrared. So what we've learned here is light is made up of multiple colors. When they're all combined together, it makes white. When you split them apart, then you see colors. Great. So if you remember physics at school, you remember that light is an electromagnetic wavelength. It has wavelengths. Click, next slide. Thank you. So we'll define light for the purposes of this talk as wavelengths which are visible to humans. And that means that it's not an objective physics phenomenon. It's not something that you can measure directly. You have to include the human being which is observing it. And that's actually quite important, and you'll see why later. So here's the visible spectrum from red to violet, or going off to infrared and ultraviolet, and you'll see some numbers there which are in nanometers, and don't worry about those. But anyway, there's a range of colors which we can see. And we can see them because of the human eye. Don't worry about all of the stuff on there that's labeled. The only thing we care about is the retina, which is the bit at the back, which actually collects light and produces electrical impulses. So stop reading those. I told you to stop reading them. You don't need to know about that stuff. The retina is made up of cells, a bunch of different cells. The ones we're going to concentrate on are called cones because someone in a fit of madness looking through a microscope thought they looked vaguely conical. Anyway, there are cones. There are in fact 3 different types of cones, and it's because of that that we have color vision. If we only had one sort, we would see in black and white, like dogs do, allegedly. I've never met one to ask. So here are the responses of the 3 cone types to light, and what you can see there is that they react in the middle range. They're very sensitive in sort of yellow-green areas. And then they're not very sensitive at reds and at violets. And then there's this other one which is so small it barely comes off the axis, which is clearly different. By the way, if you were designing a system to pick up color, this would be a really bad design. Okay, this is obviously a case of unintelligent design, also known as evolution, because two of the cones are almost the same, except for one being a bit less than the other. And the third one, we actually have to put it onto a logarithmic axis until we can see. You remember logarithms, right? You know, powers of 10 and all that sort of stuff. Okay, so there's the purple one. We can finally see it. By the way, I've colored these as yellow, yellow, green, and purple just to reinforce the fact that that's the wavelengths that they're most sensitive to you. Because of that, in crappy textbooks, you'll often see these referred to as the red, green, and blue cones. And now you see why that's a bad name for them. So, and lastly, just pointing out the human brain is an integral part of that. In fact, the retina is a part of the human brain. It's just a part that happens to be wrapped around the back of your eyeballs. The orange part there is the visual cortex. I mentioned that just so you know where it is. It doesn't actually matter. So now, audience participation time. What I want you to do is to look at that black dot in the middle of the screen, and I will attempt to hypnotize you for 30 seconds. Keep looking at it. Do not look away. Do not start scanning around or looking at the audience. Just keep looking at that for about 30 seconds. You've done 10 of them already. Keep going. Keep going. You are feeling very sleepy. Oh, no, that's the lunch. What color do you see? Green. Why? Magic. No, opponent colors, yes. Yes, it's the opponent colors, that's right. Basically, the light-sensitive cells in your retina got a bit tired from looking at the same thing all the time without moving around like they normally do. And then once they got tired, then when they saw white, some of them gave up and only saw parts of white. Let's do that again. If this clicker will move, God. Thank you. Okay, try again. 30 seconds. Look at the central dot. The reason you look at the central dot is to make sure the same part of your retina is focused all the time on the same area. Otherwise, you get less of an effect. Keep going. You know there's no trickery this time, no hypnotism. I will take 2 volunteers up on stage, though, with my glamorous assistant, who will embarrass them, yes. Any colors there? Did you get a yellow? Yes. Okay, good. So there is this concept of opponent colors. And this is very important. We'll see why later. Actually, let's go back to, well, no, it's not. I'll just look at this slide. If you saw yellow and you saw red and you wanted to mix them together, you would probably have a name for that, right? You could call it a yellowish red or indeed orange. And if you saw a yellow and a blue and you mixed them together, you wouldn't call it a yellowish blue. You've never seen a yellowish blue. Why? Because they're opponent colors, you can't see them both at once. You can only see one or the other. Let's get to the color in the middle, white. This is a photo taken in a hotel room of a piece of white paper. And I switched off the auto white balance on the camera deliberately, and it looks yellow. But at the time, to me, it looked white. And if I took it outside into the sun and looked at it, it would look white. And if I took it into the shade, it would still look white. The light levels are hugely different in these 3 scenarios. And yet my brain is capable of saying, this is a white sheet of paper. It's always white. The light levels are changing all over the place, but your brain is adjusting things for what makes sense. It's adjusting things for what's relevant and what's irrelevant information. If the sun goes behind a cloud, that doesn't matter. The view you see of the world is the same. So we do a lot of this. We adapt to what's called the primary white. And color systems that don't take account of that have problems. Humans have problems with that as well, actually. If you take away the context, if you just crop right down so you don't really know what the defining white is, then you can be led to believe that a dress is blue, when in fact it's clearly white. So color, let's define color now. It's a subjective sensation. It's not objective. It's not directly physically measurable in the brain. And it's caused by visible light acting on the eye. Well, that should make you scared by now. How are we going to define it? Because it's a nebulous, subjective sensation. Go. Thank you. Well, you should be scared, frankly, because that is kind of a dubious thing. I mean, maybe we need an entire spectrum all measured, and we need electrodes in the brain, and we need to start dissecting eyes, and No, actually, it turns out we don't need to do all that. It turns out there are a number of simplifying things which we can use and which I will show you. So science to the rescue. How do you measure color? If I hadn't forgot it in my hotel room, I would hold up a large black device like this, and I would say, this is a spectrophotometer. Just work with me here. Come on, work with me. This is a spectrophotometer. Do you believe in the spectrophotometer? Yes, thank you. You do. And it uses to measure things like this. So at every different wavelength, it measures the intensity of the light that it finds at that wavelength, and it gives you a nice little graph or a table of numbers like this. So from this, you can clearly say that this is... What color is this, by the way? Does anyone know? I didn't, unless I looked it up. This is actually a fluorescent light bulb. Who would know? It's a slide deck. Yes, so I cheated. I looked at the title. That's true. But apart from that, yes, you wouldn't know. There are ways to work out what color something is, but looking at a spectrum directly doesn't actually tell you. Let's see what we do know. If you get people and you show them a single wavelength and you get them to rate it against another wavelength and see which one is brighter, so using the human as a comparing system, you'll find that, as we saw already, wavelengths in the middle, yellow, green ones, we can see those as really bright. You should be looking at the sort of orangey line here. Ignore the dashed one, which is what happens when you're looking under moonlight, which is a bit different. So we already know that the system as a whole has a peak sensitivity in yellow-green and goes off towards the violet and the red. So that's the first piece of information we have. And we already know why, right? Because I already showed you this diagram. You basically add those three up, and that's what you get. Next thing, a visual match. You can have two colors that look identical. Right, you put them side by side, this is the same color. We're very good at telling if two colors are the same, especially if they're right next to each other. But they can have wildly different spectra, so there's something going on here. And of course, the thing that's going on is we only have 3 color channels coming out the eye, because we only got 3 cone types. So we can combine these in various ways, but at the end of the day, we don't have a full spectrometer in our brains. So they did this in the 1930s. They got 3 lamps together. They were mercury lamps. I've dropped it on the wavelengths there, but don't worry about that. Trust me, there were 3 wavelengths. And the reason they did that was because all the different labs in the world could do the same experiment because of the physics of mercury lamps. They make very narrow wavelength bands. And the idea was you had 3 sliders, and there was a color you could see on one side, and you had to match it with these 3 lamps. And they did that for all the different wavelengths all the way through, to see how much of each you needed to match. Now, are there any observants among you? Yes. Does anyone wonder why there are lights on the other side as well? You can be honest. No, you didn't. You didn't care. Okay, that's fine. The lights on the other side is because some things can't be matched. In particular, you turn the red slider all the way down, and it still won't match, so you have to actually add red onto the other side. You have to cheat and add more red to the unknown color, and then it will match. Which is fine, you just call it a negative value. Which is kind of unfortunate, especially in the 1930s when people did everything using pencils and paper and log tables and slide rules and stuff. But you can do it. So you can define a matching color with just 3 numbers. You don't need the whole spectral data nonsense. And that's good. 3 numbers is workable. We can deal with 3 numbers. So then they took that experimental data and they transformed it into a system called CIE-XYZ. CIE just stands for Commission Internationale de l'Éclairage, which means International Lighting Commission in French, which they used a lot in those days. But so ignore that part. But XYZ was a much more reasonable thing, and the first thing that made it reasonable was that they got rid of all the negative numbers, which was nice. And they did so using a thing called supersaturated imaginary primaries, and don't worry about that because you don't need to know. But in particular, of those 3 primaries, one, the Y channel, is called the luminance. In other words, it's that same function we saw about high in the middle yellow-green area. So it tells you how bright something appears. The X and Z together tell you what color it is in a way that's difficult to actually understand when you just look at the numbers. But it does. So if you've got XYZ measurements of something, you can tell, for example, what sort of white it is. You can measure what's the white from that light, and is it different from the white from that light? That sort of thing. So it's good. And it's additive. What does additive mean? So imagine I'm on a stage. No, you don't have to do that. I am on a stage. Imagine I'm standing underneath that blue light, and then there's a, I don't know, a magenta light over there, and they start moving towards each other, and they want to know what color will they make when they meet. You can do that if you've measured that one in XYZ, and you've measured that one in XYZ. You can just average the two numbers, and you will actually get the measured result. When the light pools coalesce, you'll get the correct result. That's what additivity means. It means you can do sums, you can do multiplication, addition, and things on the numbers and get meaningful results. There are some downsides, however, to XYZ. This is a gradient of luminance from 0 to 100. And I've outlined where the middle gray is, and you'll see that there's a problem with that. It's kind of not in the middle. So what does that mean? Well, it means it's not perceptually uniform. In other words, the distance apart two things are doesn't relate to how different they appear to you. So it's a good measurement, it's good for doing numbers in, it's doing calculations in, but it's not good at telling us how dissimilar two colors will appear. There's another issue. White adaptation. Remember I showed you the picture of me holding up a piece of white paper looking yellow, and if I'd had the time to take another piece of white paper looking blue in daylight. So that's white adaptation. The fact that you will see those, depending on the situation you find yourself as white, isn't handled. XYZ is great to tell you what kind of white am I seeing right now, but it's not good at saying, if we ignore all that and assume my eyes are adapted to white, what color do I really see? So we need a new system derived from XYZ, which is more adapted to human vision. And that one is called CIE-LAB. So the previous system I was telling you about dates to 1931. This one's much more recent, 1976. You can see why it hasn't caught on the web yet. It's so new. Okay, so there's the L axis of LAB, and as you can see, mid-gray has the desirable property of being right in the middle, so already we're off to a good start. And comparing that to luminance, you can see the difference there. Boop. Yes, that's where we want to be. Now there are two axes called A and B, which together, so the L axis is all the lightness, brightness information, and A and B are how colorful it is. And each of A and B can be positive or negative. If A is towards the positive end, it's a sort of pinky purpley color. And on the negative end, it's a sort of, what's that called? Teal, magenta, teal or something like that, turquoise. You'll notice there that there's a -40, which is grayed out. Anyone care to hazard a guess why it's grayed out? You can see without the eye. So good answer, but wrong. Anyone else? I did make the slide that way. Why did I make the slide that way? And you keep answering for being a smart ass until you tell me the right answer. The reason being that not that the eye can't see it, but the monitor, the projector, can't display it. It's too bright, it's too saturated. That color is outside the gamut, as they say. I'll explain gamut later. So that's the A axis, and the B axis goes from a sort of mustardy yellow to sky blue. Okay, so put those two together, and you get this sort of thing. It's a three-dimensional space where light, neutral grays and whatever are always up the middle axis. L goes from 0 to 100 very conveniently. It doesn't matter how bright it is, you just include the brightness of the reference white and scale to 0 to 100, so it's very easy to use. And then there's A and B, which, okay, they represent colors. It's quite nice, but it's kind of like jiggling with RGB sliders to make a particular color. You fiddle with it, and then you fiddle with it again, and you guess and you hope and you get it wrong, because you can sort of see it, but it's difficult to know exactly what values would give you a color you wanted. So let's put that in a nice polar form. We've got a hue wheel now with red at roughly 30 degrees. Okay, that's better, that's more reasonable. So we now have a hue angle sweeping around. We've just done a rectangular to polar conversion. And then chroma, which is how colorful it is. Sort of similar to saturation, not quite. At this point, you may be thinking, hang on, I've heard about this thing. You're selling me something I've already got. We've already got HSL, right? HSL already has a hue angle. It already has a brightness. This is the same thing. Look at this diagram and look at the yellow and look at the blue and tell me if those look the same lightness to you, to your eyes. Do they? No. They both, however, have the value of L equals 50 in this system, which is lying to you. Actually, this system came out in 1978, 2 years after the CIE system, and was an attempt to bring a similar sort of hue-angle type system to RGB with a few simplifying things, like not ever telling you what color it really is. Okay, so color displays. This is a picture of a color display with a device hanging on the front measuring the screen. Why would you want to do such a thing? Because you want to know exactly how your device behaves. What happens if you don't have that? Well, that's okay, because maybe you can't afford one. They're not that expensive, but maybe you can't afford one. But the people who made your screen certainly can, and they probably did some of this just as quality control shipping out the factory. And in fact, increasingly, you'll find that screens come pre-calibrated, pre-measured. Some of them even with a certificate if they're charging a bit more, showing what the values were. So characterization is basically you measure the color of red at different levels, and then at green at different levels, and then blue at different levels. You can do these separately because it's another example of an additive color space. And once you've measured that, you can calibrate it. You'll find that if you do a neutral grayscale, there's areas where it's a bit too blue and areas where it's a bit too brown and so on. And given that numerical data you've measured, you can do correction curves, lookup tables to give you neutral grays and to give you the white point that you want. Not a sort of bluish white that you'll get by default, but a nice neutral white. Which gets us to the gamut, the range of colors that can be correctly displayed. The actual color of full red, full green, full blue gets measured, and then you can work out what the gamut is. Now, if any of you ever gone shopping for a high-end monitor, like one that you'd use on Photoshop and you'd use Adobe RGB and that sort of thing, does anyone use such things? Any designers in the audience? I'll just go home then. But if you have done, then you'll have looked at advertising, and the advertising will have diagrams like this, which does have the merit of being in 2 dimensions and has the disadvantage of lying to you again. You'll see something with a triangle on there, and it'll tell you this monitor is wonderful because it has this shape. But this is a 2-dimensional slice out of XYZ. Remember, I said XYZ is not very good at comparing colors, and that means it's not very good at comparing the gamut of the different devices. Instead, you want to be in 3 dimensions. So here is an example. This is a top-down view of LAB space. And we're looking at the sRGB gamut. sRGB is what CSS uses, what HTML uses, is what Canvas uses. They're all defined in terms of sRGB, which in terms, again, is defined in terms of actually the reference monitor that's used for HDTV. That's where the colors come from. So there it is. I'm going to show you this again in a minute. But for now, look at that shape and compare it to a real device. Oops. This is someone's MacBook Air, which I was gently laughing at, having measured it, because, well, it's a bit small, actually, isn't it? It's not as good as sRGB, but it's okay. And then let's look at a sort of nice high-end monitor. So that's much larger. That shows you the full range of colors that can be produced, and it can produce more colors than sRGB can. And of course, this is a top-down view, but that's less interesting. What we really want to be able to do is grab hold of this and play with it and look at it in 3 dimensions. Like that, and then we can have a better idea of how these things compare. So if you actually are buying a high-end monitor and you see volume, if you see gamut volume mentioned, that's a much better measure of what range of colors it can produce. So this is a high-end monitor. This is something you can do all of Adobe RGB and display it correctly. Okay, so now we get the idea that we can look at different devices and we can see what range of colors they produce. And what's the problem with device-dependent colors is that you'll have seen this yourself. You display the same color on different machines and they look different. Whereas what we actually want is device-independent color. If it's within the gamut, it can be displayed correctly, but the trick is you have to know what values to feed the monitor. It's not going to be the same for each monitor, each screen. Now, let's see. I've got 5 minutes left and we've got CMYK. How many people are interested in printing? 1, 2, 3, not very many. I'm going to do this quickly, therefore. This is a dot screen from CMYK printing. Basically, the inks are opaque, and so if you put them all on top of each other, you wouldn't see them. So they use this dot pattern skewed around at various angles so that you get less overlap. And that's how you simulate color. So again, we characterize. In this case, though, it's different. Instead of measuring them, the cyan, magenta, yellow, etc., separately, you have to measure every possible combination. Well, not every possible, because there's loads of them. But basically, you print out a sheet like that, except much bigger, and you measure every single patch laboriously. And if you're an office junior, then that takes you all afternoon. And if you're a sort of professional print shop, you have a thing that's automated like a robot that just measures them all like this, and it's great. That's fast. And then given that data, you can calibrate it. You actually, basically, if you know what color you want to produce, you find the patch that you measured that's closest to it, and then interpolate from all the other patches and get a good result. And that data gets stored in a thing called an ICC profile. And I mention this because we'll look at ICC profiles in a minute. So that basically is that if you ever wanted to do CSS that also is used for making a book or making printed materials, you would want an ICC profile for the printer that's going to be used. Okay, finally, CSS4 color. What you may be asking, by the way, why is there a sheep? If we have time for questions, I'll explain the sheep, otherwise it will just be a mystery. So, this is what CSS3 color does for you. So let's pretend I have a high-end monitor and I've got this RGB value, and it looks fine. I'm a high-end designer. It looks cool on my monitor. I go over to some lowly peon and look on their monitor, and it's all pale. And I say, well, that's because you've got a rubbish monitor. And they are actually inexperienced, but clever. And they say, no, it's because you failed to account for the gamuts of the two devices. And I go, so I did, actually. So this is what happens now. I mean, the color I'm seeing here on the screen, the color you're seeing over there from that projector are wildly different, right? They're not a bit different. They're a lot different. So, well, what can we do about that? Well, we could hack it. That's the first response. There's a new media query in Media Queries 4 about the color gamut. So I say, okay, well, if you've got a P3 gamut, which is a sort of medium wide gamut, then I'll use this value. And then I'll go into a color calculator and work out what the value should be and say, otherwise for sRGB, then I'll get that. This is really horrible, isn't it? This is ugly. Do not ever do this. This is just me showing you what you'd have to do. And how different the values would be to get the same color. Yeah, you get the same color, but it's ugly. And what happens if there's a third monitor, a fourth monitor? If there's a projector, it's not going to work. Instead, use this LCH, derived from LAB. You've got lightness, chroma, hue angle. The browser itself works out what the RGB value should be because it knows what your screen is. And then you get the same color on every single one. That is the point of using it. Also, the fact that you can get physical devices. You can measure something and say, what color is this suit? And that sort of thing. What color is this shirt? And then you can put that straight into your web page. So that's pretty handy. Let's look at the syntax now. So there's LCH. It just takes three numbers, L, C, H. Pretty simple. If you put a comma, then the next value is the alpha. And if you put another comma, there's a fallback value. So you can give for older devices that don't understand it or that don't have color management systems, you can give them a fallback value in sRGB. Same for LAB, which you can use there. It's again 3 parameters. ICC color, so you can actually say I'm using this predefined color space, DCI-P3, which is a wide gamut monitor, and Rec 2020, which if you use that now, good luck to you, because that's a massively wide gamut monitor that people are having real difficulty making, but in the future it will be more relevant. The broadcast industry is using that. We picked these 2 standards because they are standards, so there's no point in defining something else. They already exist. And lastly, Media Queries 4, but I already mentioned that. Media Queries 4 can help you there. If you are actually going to a printer, then there's an @font, like the @font phase, there's an @rule called @color_profile. Where you point off to your ICC profile and say, okay, I'm defining this color, and I'm going to use it in CMYK. You see there's 4 parameters there, CMYK, and I can say that's my color. Why would I care about this? Because this is an actual measured color. I can convert it to LAB. From LAB, I can convert it to sRGB. That means I can do things with this, like composite it. I can use it in my screen and get the right value, get the right color. It's not one of these style sheets that only works in print and doesn't work on anything else. Yes, I know I'm out of time. I'm almost there. Can I use it? Well, this is great, Chris. Can I use it? No, you can't. Actually, this is brand new, really brand new. It is not in the browsers yet. It was only agreed in San Francisco like 2 months ago. at the meeting we were at. The first public working draft is published next Tuesday. So you've got kind of a scoop here. But really, when you look at the draft, you'll see the syntax. And the syntax will you'll say, OK, LCH parentheses numbers. Now you know why that's relevant and important. There is some more online. The slides are on GitHub. The specification itself is on the CSS working group site. There's also some code which I wrote which does color conversion, so if you want to poke around at that, you can have a look there too. Thank you very much.
Thanks, Chris. So we have time for questions. Yes.
Why the sheep? OK. In the early days of the CSS working group, when we were trying to get from CSS2, which was ambitious but poorly specified, to something that people could use, I started complaining whenever anyone did hand-wavy stuff about, well, this does, the auto value does whatever it sort of does in the different browsers. I go, nah, that's too woolly, let's shave off all the wool. So this idea of a sheep was born, that the sheep had to have all its wool taken off, remove all this wool from the spec. And eventually someone drew one, and then it became a kind of unofficial mascot of the CSS working group. So there we are. You know why it's still woolly, Charles, because the spec is still woolly as fuck.
Sorry. I know this might be an annoying question, but can I technically keep using RGB and then just use something at compile time to make it look the same on every monitor?
Yes. If you have the data for everyone's monitor, then you can do that on the server. Also, if you have the data on anyone's monitor, I want to know where you get it from, because I'd like to get a copy of it.
No. Isn't it enough if I have data on my monitor and then I can convert everything from RGB automatically to these better measuring systems that you described?
Yes, sure, you can do that. Yes, absolutely. Okay. Any more questions?
For a designer, which tools designers have to measure those specific measurements of color?
Okay,
today?
well, if you're working...
I believe if it's a new feature, so I believe Adobe still doesn't support it.
Right, so if you go into Photoshop, for example, you'll see there's an option to set the mode to RGB, CMYK, and LAB. And so you can convert to LAB. You do need to tell it what the monitor is. It needs to be color managed to be able to do the conversion. So you can work like that. More interestingly, there are devices called spectrometers. So like a color monkey is a cheap one. And it's physically a device. And you can hold it up to a light, and it will tell you what color it is. And equally, you can put it against a physical surface. It has a light inside it. It reflects off the surface, measures the color, and gives you a readout in LAB. So you can actually physically measure. And because it's LAB, that doesn't matter what the white was of the LAD and whether it's different from your monitor, because they've been adapted to each other using a thing called the Bradford chromatic adaptation transform, which means that you'll get a reliable color. Don't worry about that. You don't need to know about it. It's been done for you is the point. LAB does it for you. So you'll get a measured color, and you'll be able to stick that in your style sheet and see, I want this color and that color and that color.
Great, thank you.
You're welcome.
More questions?